We are thrilled today to have Professor Amy McGovern, who is a Laura G. and Joyce Austin Presidential Professor in the School of Computer Science and the School of Meteorology at the University of Oklahoma. During her assistant professorship before that, she won the prestigious NSF Career Award after a PhD in computer science and postdoctoral research at the University of Massachusetts Amherst, where she also got her Master of Science after a Bachelor of Science with honors from Carnegie Mellon University. Professor McGovern's research focuses on developing and applying machine learning and data mining methods for real-world applications, with a special interest in high-impact weather analytics, and physical data science. Her laboratory developed physics-based trustworthy artificial intelligence methods as well as explainable AI, and applies these methods to high-impact weather phenomena, including tornadoes, hail, severe wind events, flooding, drought, and aircraft turbulence. And after leading the development of AI and machine learning for weather applications for 15 years now, Professor McGovern just launched and is now directing a very new NSF AI Institute for research on trustworthy AI in weather, climate, and coastal oceanography. And with that, please give a warm welcome to Professor McGovern. Thank you.
All right, hello, thank you. And sorry for the technical difficulties. The cable internet went down about a half hour before the talk, so I am hotspotted on my phone. So I thank you. You already said everything that I was going to say on this slide. So go ahead and what we're going to talk about today is we're going to talk about building the trustworthy AI for environmental science, which is part of building our new NSF AI Institute. And I actually noticed on the participant list that our NSF program manager is listed as an attendant as well. So maybe if he has questions too, we're going to all answer questions here. Go ahead and go to the next slide. Because I'm hotspotting, I had the slides sent over because I was afraid it wouldn't be able to send my video and the slides all on my iPhone. So motivation for what we're doing. This part is probably preaching to the choir, but I'm going to do it anyway because I want to give the full motivation behind everything we're trying to do. And I'm trying to talk about the general, not just our NSF AI Institute, but also the motivation for why we need AI for environmental science in general. So go ahead and hit the first animation. You know, we can't control the environment. That's a picture from a tornado that hit a house and clearly destroyed it. We're not going to be able to stop the tornadoes, but as the climate is changing, we may be getting more intense tornadoes and more frequent tornadoes, and we would like to be able to improve both our prediction of them and our scientific understanding of them. Go to the next one. That's a related picture of another event we're not going to. Hopefully sound will work now. Okay, so the third impact here, this is something that's not necessarily the severe weather. This is from our colleagues at North Carolina State. They're going out and sending out probes to measure different things in the ocean. And in particular, this one's working on measuring ocean eddies, which we're going to talk about in a couple of slides. So I'll leave it at that. Go to the next one. Another impact in the way that we might not necessarily think about our resiliency is looking at the impact on ecology and biology. So this is a picture from one of our colleagues in the Institute of the sea turtles and working on the impact on biological life. So if we can use, as our climate is changing, the impact on biological life is tremendous. And the example that we're going to use is using AI and developing AI that can be used to save the lives of the sea turtles. And I'll talk a little bit more about that in a little bit. And then go to the last one. And again, just another picture of an impact that we're not going to be able to control, but if we can improve our understanding of it, we can dramatically improve our resiliency. Next slide. So presumably that part everybody understood well because this is the climate group. But you know, if you want to see another set of motivations and you'd like to look at the money, the number of billion-dollar weather disasters has been going up. I didn't put the graph of how much they're going up year by year. Instead, I just decided to focus on the graph of what 2020 looks like because I think this is embedded in everybody's head. Everybody just says, oh, it's 2020 again. It is. There have been a tremendous number of billion-dollar weather disasters this year. And again, we're not going to stop these disasters, but if we can improve their prediction, then we can make them less impactful. We can save property and we can save lives. Next slide. So the other half of this motivation is that, you know, the reason that we need AI, we can't just do this with the foundational science. Why do we need the AI and the foundational AI, and why do we need to develop the new AI, is that we have a tremendous amount of data that is coming online. We have a data overload. There are new sensing systems that are coming online. They're providing unprecedented high-resolution data. We have new satellites that are providing data every 30 seconds, every minute, every couple minutes. It's a lot more than they used to be doing. We have mobile radar trucks that are out there providing data. You have crowdsourced data and much more. And you need to be able to sift through all this data and identify what's actually important and what really matters. And one of the citations that I have in a different paper talks about the fact that we really only use about 5% of the satellite data right now. And if we could imagine that the tremendous amount of that 95% of the data that we're throwing out right now is actually useful, if we can use AI to identify what's most useful, we can use that to improve, again, our fundamental science and our predictions. Next slide. Finally, I said that this is leading us to the point where we're developing AI, but we're developing trustworthy AI, and we need to care about the humans at the other end of this. We're not just developing AI and throwing it over the fence. And our humans are making critical decisions. Forecasters are often making life or death decisions. Do they evacuate a city for a tornado warning? Or do they issue a tornado warning? Do they evacuate a city for a hurricane? Do they issue go, no go for a launch? And that's the picture that's down here from the SpaceX launch. That's this summer where they called no go about 3 minutes before launch. These are life or death decisions. And if you're basing your life or death decision on an AI product, you want to make sure that your product is trusted. Now, the different end users have different needs, and forecasters are often making these life or death decisions. Emergency managers are making different needs at a different time scale. Are they closing a business early? Are they sending the buses out on the roads? And then if you even go a step back to a completely different set of users, you could look at farmers, for example. And farmers want to know in a longer time scale, is it not going to rain over the next 2 weeks? Are we about to have a flash drought? Or, they might care about the hail because the hail is going to destroy their crop. And the needs of the end users here for the farmers matter. Their needs differ if they are corporate or if they are family owned. Because the family-owned farms are typically smaller and running on a much smaller margin and can afford less mistakes. So the trust of each of these end users is going to determine what their needs are, and the AI that we develop needs to be tailored to those needs so that we can actually gain their trust and give them an AI product that's actually going to improve them and improve the predictions and improve the understanding. And I didn't talk about the scientists as end users, but we are looking at the scientists as well. Go to the next slide. So the new NSF AI research, or NSF AI Institute for Research on Trustworthy AI and Weather, Climate, and Coastal Oceanography is the institute that I'm going to be mostly talking about for this, and I'll be glad to take questions at the end about it. We have the list of all of our, I wish I had my own mouse control, but I can't, and now I don't even have my videos. Can't even gesture. You can't see that I'm talking with my hands, but down the right-hand side of the slides, we have all of the university partners with OU as the lead. And then down the bottom in the lower left-hand corner, we have our private industry partners. And then we have federally funded research center of NCAR. And then we have a government partner with NOAA. And you can go to our website and learn much more. And over the next few weeks, we're going to be populating the website out with the remaining sections that are actually required by NSF. But there's a lot on there already. And then we have a Twitter handle, and you'll be glad to see as many of you following us on Twitter as you want. There's not a whole lot of tweets yet because it's just me running it, but there are going to be more tweets as we start doing more things. So what our institute is doing is, when I'm calling it AI2ES for short, AI2ES is going to uniquely benefit humanity by developing novel, physically based AI techniques that are deemed to be trustworthy, directly improve prediction, understanding, and communication of high-impact environmental hazards. And what I want to do for the remainder part of the talk is talk about what that means. So next slide. So we have 4 foci. And for the purposes of this talk, because I don't have a whole lot of time, I'm only going to talk about the first 3, but I wanted to mention the 4th one at least on this slide. We have a synergistic cycle here where we're going to talk about the foundational research in trustworthy AI and machine learning, the use-inspired research in environmental science, and the foundational research in risk communication that feeds back into the AI research, because we're actually looking at the end users and making sure that we're developing trustworthy AI. And then the component I'm not going to talk about so much today, although I'll be glad to answer questions about it, is the broadening participation in workforce development, where we are actively working to bring AI and environmental science and improve the diversity of all of the participants in that. Go ahead, next slide. Okay, so let's start with the foundational research in trustworthy AI and machine learning. We have 3 big goals here. We want to work on developing explainable AI methods, and these AI methods need to be aligned with environmental science domain perspectives and priorities. And partly, I want to talk about that a little bit on the next few slides. What I want to say is that AI traditionally studies different data than what you see in environmental science. So you're studying data that is typically not autocorrelated. It's not in space or time. It's not got sparsity issues or, issues. Typical AI has not got issues where if you make a mistake, you might kill people. There are a variety of reasons why the AI for environmental science is very different than traditional AI. And so we're going to be developing explainable AI methods for that data and developing physically based AI for environmental science. And then as a third part of this, and they're all intertwined, we're developing robust AI. So everything that we do is going to be theoretically and empirically validated. And we want to be able to say that the AI methods are robust. Next slide. So I'm just going to give you an example of what we can do with XAI and environmental science. And I think from looking at your working group and knowing that Emma is here and that Libby is here, you know some of this part already as a working group. But I'm going to go over it briefly. So the leftmost example here, the emulating radar imagery with CNNs, is actually from Emma and Libby. And here, this is work that we're using deep learning to train a network to mimic the radar given only satellite data, because you can get satellite data in places that you can't get radar data. And then once you've trained it, we're using XAI to make sure what it's actually learned is something that's physically plausible. So in this particular case, it's, for example, identified areas with gradients in the cloud boundaries or high brightness in the cloud boundaries, both of which make sense and are important to doing the radar predictions. The middle example comes from the work of a former student of mine, David Gagne. And here we're working on predicting hail. And what he's done here is not just looked at improving the prediction of the hail, but try to look inside the network to make sure what the network has learned makes sense physically, and might be able to identify new hypotheses. And in doing so, he looked in there and he said, well, this looks like, and he's going to put human labels on it, this looks like a type of supercell, a type of bow echo, and a type of pulse storm inside the network that it's learned. And we want to see where those show up geographically. And what happened is that, in fact, they do show up geographically approximately where they show up climatologically, that you get the supercells, which are shown here in red, in Texas and Oklahoma, which is where they show up much more climatologically. And the bow echoes more in the upper Midwest, and the pulse storms more in the Southeast. So the network has learned something that makes physical sense. For the sake of time, I'm going to skip the third example. So go ahead to the next slide. So I said that the XAI is related to the physically based AI. We need the XAI to create, we need to create XAI that works on environmental science data, and we need that XAI to be based in physics. And so we also need to be developing machine learning methods, not just XAI, but machine learning methods in general that are based in physics. We need to be able to understand that fundamentally everything we're doing in environmental science, weather, climate, and coastal oceanography, are all physics-based domains. And we want to integrate those physics into everything we're doing. So integrate the physics into the feed-forward networks and integrate the physics into the XAI that we're developing. Go ahead to the next slide. The third part of the AI is looking at robust AI. So here we care about robustness, both theoretically and empirically. And I want to talk about a couple things that are unique for environmental science data compared to sort of your traditional AI data. So first of all, many of the events that we actually care about are very rare. Even if you're in a bumper crop of a year of tornadoes, we have a very small number of tornadoes in a year. When we are used to, deep learning really wants to have thousands of examples or tens of thousands of examples. We're not going to get that in tornadoes. We're not going to get that in hurricanes. This has been a bumper crop of a year of hurricanes, and we only have tens of hurricanes. And we don't want thousands of examples, by the way. I'm not asking for that. What I want to do is to have us develop methods that we can theoretically say are going to work robustly, even given the small number of examples. And now another thing that happens with environmental science, and then in computer science, they often talk about adversarial data, where there's an adversary that comes along and corrupts your data. In environmental science, the environment is the adversary. So I have an example here of a mesonet storm where we had a wind gust of 151 miles an hour that got recorded at the El Reno mesonet. And if you were developing an AI method, machine learning in particular, that was using this data as the underlying data, you might be tempted to throw this out as an outlier. But in fact, it was a real data measurement. So we need to be able to develop methods that both identify when it really is an outlier and throw it out and don't let it throw off the predictions, but also know what to do and not go crazy when you do get an outlier like this, so that you actually get a physically based answer that you can trust. And in case you think it might have been an outlier, there's a picture of the mesonet station of what happened to it after that when Gus went through. It really did happen. Next slide. Okay, so the second part of this circle is that we've done the AI. We're going to talk about the environmental science application domains that we're going to do, and then we'll talk about the risk communication, and then we'll probably be just about out of time. So go to the two goals before we go to the next slide for the environmental science applications are that we're going to use the trustworthy AI to provide actionable information to a diverse set of end users, and then we're going to use this AI to enhance our scientific understanding and physical understanding of the environmental science processes. Go ahead to the next slide. We have 5 application domains, and I want to talk briefly about all 5 of them. So the first one is convective weather. And here we're primarily on this slide talking about tornadoes and hail, but we are looking at other convective hazards, including lightning and wind. Thunderstorms already produce a tremendous amount of damage. They kill people every year. And we are, again, as I said at the beginning, we're not going to be able to stop them. But what we can do is we can improve our prediction and our understanding of them. And by improving our understanding, we can thus improve our prediction. And so I have 2 examples here from some work from my group. The one on the top right is an example from a PhD student of mine, Ryan Lagerquist. He just graduated and now he's a postdoc with Emma. And here his work, he was working on using deep learning to predict tornadoes over the next hour, given data that would be available in real time. He wasn't actually doing it in real time. He was doing it retrospectively, but the idea is that we will be able to do it in real time. And once we've got the predictions, we wanted to look inside the predictions to make sure that what it had learned was physical. And when we were able, this turned out to be a great case for showing us where we really need the physics constraints in what it learned, because it was learning things that weren't physically constrained, and we need to be able to constrain what it's learning so that we can improve the trust in the output. And the second example is another good example of that. We've been working for a number of years on predicting severe hail and hail across the United States using a variety of AI methods. And when we do these predictions, sometimes the forecasters say, oh, that's too high of a probability, and so therefore they don't trust it. And one might be tempted to say, well, if the event actually happens, why do you care that the probability is high? Well, it gets back to the question we asked earlier, which is that the end user needs really, really matter. And the hail has provided us a tremendous amount of feedback from our end users, so it's getting us a jump start on the idea of knowing that what we develop has to matter to the end users. If they're going to trust it, we have to know exactly what their needs are. Next slide. The second domain is winter weather, and winter weather causes major hazards across the whole United States. We're going to be studying it in New York and Oklahoma. And both states get both snow and ice events during the winter. And they have both states have a unique observing system, the Oklahoma State Mesonet and the New York State Mesonet. The Oklahoma State Mesonet's been in existence for about 25 years. The New York State Mesonet's about 5 years old. And they have a tremendous amount of observations that they're recording every 5 minutes about all of these events. So they give us a unique data set that we can use to study this and develop the AI methods to improve the prediction and understanding. Go ahead to the next one. The third environmental science application domain is tropical cyclones. And here I'm going to give an example of how we could use XAI to improve our understanding of tropical cyclones. So for example, on the left-hand side, you've got a hurricane, and you can study the internal structure of the tropical cyclone using the microwave imagery, but the microwave imagery is only available a couple of times a day. You've got geostationary satellites that have the data available much more frequently, but they're not giving you microwave imagery. If you can train a network, a deep network in this case, to mimic the microwave imagery given the satellite imagery, you can create simulated microwave imagery available every 10 to 15 minutes. And then you can use the XAI to make sure that what it's learned is actually physically plausible. And then you can generate this data, and you can use that to improve your understanding of how rapidly tropical cyclones are intensifying, which is something that has happened a lot this summer. So go ahead, next slide. There we go. Okay. The fourth application domain is looking at subseasonal to seasonal prediction. Here we're looking at the gap between the ability to predict weather over the next 2 weeks and the ability to look at seasonal, which is really 2 months to 12 months. There's a gap. There's a question. What can we predict in that 2 week to 2 month time frame? And this is Libby Barnes's work. So I don't know that she's on today, but I want you to, I know that she's part of your group. These results in the lower right-hand corner are hers. Here we're looking at, can we use machine learning and AI to improve our understanding and our prediction of weather in that gap. And here's an example of looking at regions that are relevant for the prediction of extreme rainfall events in North America that happen 18 days later. And you'll note that that's not North America. We're looking at Asia. So we're trying to figure out which regions are most important. And this is showing a heat map of the regions that are most important. Go ahead, next slide. The last application domain is coastal oceanography. And here we have a tremendous amount of applications. The first, we're looking at ocean eddy shedding, and I was talking about that with the probe at the beginning. Ocean eddies are very large-scale circulations. They have been called ocean tornadoes, but they are nothing like a tornado in time or space scale. They last for several months, and they are much larger in space. And we need to be able to improve the prediction of knowing when they're going to form and when they're going to dissipate, because they impact everything on the Gulf. The next application domain in here is harmful algal blooms, which I think a lot of people have heard about from the news. They are killing a lot of biological life, and we need to be able to improve the predictions of those. The third is the compound flooding. And if you go to the next slide, I have two more. So I promised I would talk about the sea turtles. The sea turtles are the fourth part of the coastal oceanography. We already have, one of our partners already has early results showing that we can use AI to improve the prediction of these events. So what happens with the sea turtles? These are in the Gulf of Mexico, specifically in Laguna Madre outside the Corpus Christi area. When it gets cold, which it doesn't do very frequently there, the sea turtles rise up to the surface. It's called a cold stunning, and then ships run them over. And so if you can improve the prediction of when it's actually going to get cold and the turtles are going to rise up, we're not going to save the turtles unless we can stop the ships. So if we can have trustworthy AI that the ships actually stop their traffic, then the turtles have a chance to wait until it gets warm and they can go back down and the ships can start back up, and you've saved a tremendous number of turtles. And in another method, in Corpus Christi, we're also looking at coastal fog prediction, which also matters for the traffic. Corpus Christi is a very busy port. It's one of the busiest ports in the United States. And if we can create trustworthy AI that can help with the traffic, we can improve the commerce there as well. Next slide. Okay. And I don't know if I have to end right at 2:30, but I am very close, just FYI. I know we started like 2 or 3 minutes late. The third part of this cycle is the risk communication. And here, the risk communication is the critical part of the cycle, because we could develop the AI and we could work with environmental scientists, but we really need the social scientists to understand exactly what it means to make this AI trustworthy. We need to understand what's going on inside our users' heads. And that part is, it matters tremendously. So the three goals for what we're working with on risk communication are to increase our knowledge and understanding of how the transparency, explanation, and reproducibility and representation of uncertainty influence trust in AI. We want to develop models of how we're going to estimate the attitudes and perception of AI trustworthiness, and then develop methods to inform the development of these trustworthy methods. So basically, we're going to be doing a lot of interviews of our end users and using those interviews to change what we're doing and what we're developing in the trustworthy AI. Go ahead to the next slide. So the relationship between trust and accepting technology is really complex. There are a lot of people that are working on it, and I don't know if anybody has seen the new executive order that came out of the White House just a couple days ago, but the White House has just signed a new executive order on the need for the government to do trustworthy AI and to use trustworthy AI. And there are, beyond our NSF Institute, a large number of initiatives at different government institutes. NIST is developing a standard for what it means to be trustworthy in AI. In order to meet that standard, we really need to understand the needs of our end users. We can't just hand them a method and say this works and you need to believe it. We need to understand why they will believe it, why they will use it. Will they use it in times of emergencies? Will they use it in times where there's less emergencies? We need to understand all of this. And so we're doing this through our social science research and by having them do the interviews of a variety of different end users. So if you go to the next slide, I have a list of some of our end users that we are looking at. This is not all of them, but it just shows you the variety of end users that we've already got engagement with. The Weather Service that looks at forecasters. We've got emergency managers, Department of Transportation, Port Authorities, Army Corps of Engineers, the EPA, and the USGS. And then that doesn't even include the fact that we're looking at scientists. And then through our private industry, we're also looking at the general public. And we'll be doing all of these experiments to understand why they trust it, and then doing things like varying our AI and seeing how that causally affects the trust on the users. Next slide. I think I said I was going to stop here in terms of how the time goes, but I will just briefly say, in addition to a lot of the things we're doing with all of the research there, we are developing, we have a robust education and workforce development plan and a broadening participation plan. And one of the things that we're doing that's unique, which I think is the next slide. Yes, one of the things we're doing that's unique is that we are creating a community college AI certificate. And this is being done at a Hispanic serving and minority serving community college, where our goal is to get more minorities involved in AI and environmental science and interested in this. And then if through this community college workshop or community college certificate, they can directly feed into either internships, jobs, or getting their bachelor's degree by going to TAM-UCC, where the community college that we're working with has a direct relationship and a direct partnership. And then we're planning to spread this nationwide. And I think the last slide is the next slide so that I can answer questions. This is a picture of the team. So I think some of these faces should be familiar. The people who are the leaders are at the top of each one of these sort of pillars. And then the names of the team are down at the bottom. And I don't think the next slide is the standard NSF acknowledgement. I think if you want to flip there so that you can see that I did them, but we don't have to stop there. I can answer questions and stick around on any slide that we want.
Okay, great. Thank you, Amy. I do see a question from Galen in the chat box. Do people understand how a weather model works? Does that impact their willingness to heed a forecast? Do users care if it is AI versus a traditional model?
That's a whole variety of fascinating questions. I'm going to give answers to all of them. Let's see. Do people understand how a weather model works? It depends on what people we're talking about. I'm not going to make Jenny flip slides back and forth because that would be hard. But we did have a list of a set of potential end users. You know, the forecasters certainly understand how a weather model works. But if we're talking about the general public, no, I don't think they understand. Does it impact their willingness to heed a forecast? I suspect it does, but that is something that we will need to test for sure. And do they care if it's AI versus a traditional model? Again, I think it's going to be very dependent on the end users. Some of the forecasters do care. Some of the forecasters definitely don't like AI. They don't want to trust it. Some of them are more willing to try new technology. And I think that's probably true of all of the variety of end users. And from our preliminary work, I think what it's going to take is that we're going to have to show that we are really developing AI that they can trust, that they can see a history of its predictions and how well it's doing in whatever their needs are, and that we're meeting their needs, and also that we're working with them. I'll give the example from the hail world. We've been working on the hail predictions for about 6 years now, and we've been working with the forecasters who are using our model for about 4 years, and we've been changing our model in response to their needs. And I think that they have seen that we're doing that, and thus it is becoming a more trusted model. They've had 4 years of seeing that. Even though the model is changing every year, they're seeing that it's changing in response to what they're asking every year. And we would be doing it at a more frequent basis, by the way, but we only get to test in the spring experiment. The spring hazardous weather test bed is when it hails most frequently every year in April, May, and June. I hope that answers the question. It's a complex question. And I don't know if you want to just stop sharing slides, we can go to seeing each other. I don't know.
Sounds great. If anyone else have questions, feel free to type in the chat box or use the raise your hand feature. A question by Bowley. Can you elaborate more about how to use AI to handle extremes?
So extremes like doing predictions of extreme events like tornadoes, or are you looking for I can think of doing extreme value computations as well. So I want to make sure I answer the right question. Maybe type
so maybe my question is, first I wanted to understand what kind of extreme value analysis you are doing. You are doing prediction, or what kind of because as you mentioned, there are not so many observations in the extreme value, but you wanted to have a robust still AI analysis. So how do you?
Right. So the extreme events that I've been looking at typically tend to be rare events like tornadoes and hail and strong wind events, right? If you want to talk about lots and lots of data like temperature, that's boring. And there's lots of that out there. I would say, so the technical answer to your question is more of developing how we're developing methods that can handle very rare amounts of data. The extreme, in terms of extreme values, like the wind example I gave, where it's 151 and everything else around it is in the 30s, is not my work, and I don't have a good answer for you. I can give you the answer on the tornado and hail, which we've been doing a lot of sampling to make things robust, as well as we've actually, perhaps surprisingly to some physical scientists, discovered that doing data augmentation has improved our results. That's not surprising to computer scientists, but the data augmentation can be unphysical. So we've had to play with the data augmentation in a way that it's physically plausible, but it basically gives us more synthetic examples. And then the models, unsurprisingly, once you have better data, the models give you better results.
Oh, okay, I see. So you use some like data augmentation algorithm to kind of generate some synthetic data to increase amount of data to apply for the AI techniques. Is that right?
For the tornadoes and the hail, we have done that.
Okay, got you. Okay, yeah, that makes sense. Thank you. I was curious how you did.
And I see a question from Pierre. Did you want to elaborate more on your question, or do you think it was answered?
And sorry for the background noise. Yeah, my kids are in the back. Yeah, so great talk, Amy. So I was actually wondering if for extreme events in particular, if you're looking more at the architectural change or if you're looking more at the data, and you talked about data augmentation. So I think there are different ways you could approach that in a sense.
I agree with
I'm just
that.
curious. Yeah.
I agree with that, and I would say the answer is both. And I think that that's one of the things we get out of having a large institute with a large number of people working on it, right? We've worked on the data, but there are others in the group who are wanting to work on the architecture.
Great, thanks.
Okay, question from Tom. I see your hand is raised. Do you want to go ahead and unmute yourself and ask your question?
Sure. It is a broader question. I was curious about what are the recent XAI explainable AI methods you're most excited about, and what would you go to XAI methods be at the beginning of the center?
That's a fun one. I just learned of a new one last week. And so of course it's new and shiny, so I'd be interested in it. It's supposed to be a replacement for LRP, and it's supposed to work much better. But I also, the other one I've been interested, I have a postdoc who's starting in a month. And so you're sort of asking the question of what's he going to tackle first, right? I'm going to give him a bunch of reading. I already gave him one paper. One of the papers I gave him that I'm pretty excited about actually uses LRP as the underlying method, but it uses TNSE as well on top of it. And the cool thing that it did is it does regime finding. And I actually think that could be really cool because you could work on using the XAI on top of that to find scientific hypotheses. So that's where I'm hoping the postdoc is going to jump in.
Out of curiosity, what is the name of that new replacement for LRP?
I can get you the name.
I didn't mean to put
Send
you on
me
the
an email and I'll send you a link to the paper. It's on the desktop, and since I'm still stuck on my laptop, I can't get to my notes.
Is that
Sounds perfect. Thank you.
The optimization of integrated gradients that you sent me last week?
Yes, it is the one. I texted it to Emma.
Okay, I will put it on the pad.
And there are two papers. There's one the one I sent you is last year's paper. The person I was meeting with last week who was telling me about it said that they just had their AAAI paper rejected, but all of you know that AAAI rejects a lot of good papers, so I don't take that as a sign against them. So they said there was a new paper coming out onto arXiv relatively soon. It's a good question.
Do you want to elaborate, Amy, maybe on the ones that you have found to be the most successful XAI techniques so far?
Sure. I mean, I think you and I actually have different answers to that because you really like LRP, and Ryan found that the backwards optimization was really cool, and then he's developing, and someday we'll get the paper out, some statistical techniques on top of that, on top of saliency maps, GradCam, and backwards optimization that he can use to verify that what's being done is both statistically significant and also the techniques are physically plausible. And so I found that to be pretty exciting. I know that you didn't like the backwards optimization results, but I actually find them to be pretty enlightening because what we're able to see is that we can generate physically plausible answers of what the network actually considers to be an optimal tornado or an optimal non-tornado, but that they're not quite there yet, right? They're getting there. And it gives us hope that if we can improve the understanding of the physics, that we can actually generate really physically plausible examples.
If I may jump in there, I think the reason why you like certain methods more than others is that we look at a different type of applications.
That's fair.
And so, because we have a lot of image-to-image translation, LRP helps us more, and the optimal input didn't work well for us. But I think because you do more classification problems for you, those are much more in GradCam, and all those things work for you, but they don't work for me. But that's not because we have different opinions. It's because we work on different types of applications. And different types of applications call for different kinds of explainable AI methods, I think. Just my take.
Yeah. And I think that the upcoming, I mean, I don't think any one of them is the answer, the end all and be all, right? And we're going to develop more of them, and they're all going to have different applications and different needs. And that gets us back to the trustworthiness, right? That you like the LRP better because it meets your needs better. I see there's another question in the chat. People developing AI algorithms that continue learning as conditions change through data assimilation. I'm thinking specifically about the HAB application where we might expect big changes in HAB events with coastal ocean warming. Yeah, so I think that's a really important question, is learning as the climate is changing and learning on data where the underlying distribution is not static. Yes, I think the answer to that is yes. It's something that we've talked about a bit, and we've been talking about. So, I mean, I'm leading the Institute. Not all of the work that I just talked about is mine, clearly. And so the work that I tend to fall back on is the work that I know best, because it's the one that's been with my students when I answer these questions. So I don't know as much about the HAB, but I would also wager that this matters on the hail, because we've been having the discussions on the hail data and the fact that hail and tornadoes might have different distributions over time, and whether or not we need to retrain and accommodate for that. And so I think the same answers will matter for the HAB. We definitely need to be developing methods that are robust as the conditions change, and that's part of the robust part of the AI. And thank you, Emma, for putting the paper into the chat.
Do we have any other questions for Amy?
Y'all are good at asking questions. Jenny told me that you would, and you are. I'll say something while they're formulating a question. Almost all of us are hiring postdocs, and we would really like to improve the diversity of the pool from which we are hiring. So if anybody has any spectacular students, and if they are diverse, we would even love to know it more. I want to know if they're spectacular no matter what, but I'd love to have you sending. And grad students. Emma's right. We're hiring grad students and postdocs. So send your fabulous students our way.
To add on that, though, Amy, if you want to send them to me, I can include them in our US Clyber monthly newsletters, the newsgrams. It's where we advertise all our webinars, including this one, and we also advertise postdoc positions.
Great. I think Emma's the one hiring next, so we'll make sure we get your ad out. I just hired. He starts in January.
Perfect. All right, I don't see any movement for questions, so I think at this point we'll just go on into the closed working group discussion. So thank you, Amy, for your presentation and for your patience as we work out the technical difficulties. And thank you to our participants today for listening in. A recording of this talk will be available within the next week or so, and then we will reconvene on January 25th for our next data science webinar.